You know what's nice about life? What's nice about being human is how easily we learn and enjoy learning from things. Have you ever wondered, what could you learn from a turnip? Or from an old potato? Or a jicama? Or some Swiss cheese like this? It's nice to know that actually you could learn a lot from a piece of potato. Anyways, we'll leave that aside for a while. Today we're doing volumes, and the first principle that I wanted to talk about was this idea of first of all, defining a volume. The way we will define a volume, we will define it for cylindrical shapes. That's shapes that they have some sort of area on the bottom and exactly the same area on the top, and exactly the same area on the cross sections. If you were to take any cross section in the middle, they're all identical. So when that happens, we call that a cylindrical shape. And we will define volume for such shapes as following. The volume is equal to the area of the cross sections times the height. Okay? And that principle stands its ground fairly well for so many shapes. You could have, for example, on the bottom you could have, let's get our little potato out of the way. Whoa, these potatoes leave stuff on the screen. That's not good. Learn something else, huh? Alright, so this principle stands fairly well for many different shapes. For example, suppose you had a square on the bottom, and so every cross section is in fact a square. Then again, the volume would be the area on the bottom. That would be this area, which is the same as area for all the cross sections, times the height, where this is the height. So for this case, if this side is say A, and this side is also A, and this side is C, the area on the bottom would be a square. And so the height is H, and so the volume for this particular one, the volume would be area times the height, which is equal to A squared times H. There you go. And it could work for a million other ones. You can just imagine the different shapes that we could have. For example, you could have a pentagon on the bottom. So long as all the cross sections are the same, so long as all the cross sections are the same, the volume will be, as I said before, by definition, the area on the bottom times the height, where this is the area on the bottom and this is the height, and it's understood that the area is the same on all the cross sections. It gets even better than that. Okay? So here's another playful question that we can just entertain. What if you had the same sort of scenario here, some area on the bottom, but this time it was the same height, but it was slanted, kind of like so. Oh, there you go. If it was slanted like this, the question is, which would have more area now? The one that's straight up like this, or they both have the same height? If you measure it this way, H have the same height, and they both have the same area on the bottom, A. The question is, which one would have more volume? The one that's slanted, or the one that's upright? Okay, and that question is interesting until you may have already seen it before in a previous math class, but the answer is it really doesn't matter. The slantedness does not change the volume. So very much like if you have a bunch of, this would be what's classically known as a cylinder, if it didn't have the hole. But just ignore the hole, and this is what most people would call a cylinder, the overall shape. And it's easy to observe here that if you were to slant the cylinder like that, I think it's easy to see that the volume wouldn't change. The volume would not change since you still have exactly the same amount of material, right? Hasn't been stretched or compressed, which would definitely change volume. All it's been done to it is slanted, and so in fact you could slant it all sorts of curvy ways like this, and none of those things would change the volume. So that's the first principle to observe here, the fact that slanting does not change the volume. In fact, if you've paid attention before, or many of you may have seen it before, if you've been hanging around the right people, you've seen that this sort of scenario. For example, if you have a rectangle, you know that the area is equal to base times height, and then you ask the simple question: what would happen if you slant this? And you still have the same b, and this length right here is still h. And the question is, how does this area compare to that area? And the area here is still base times h. So this is this would not be from the volumes chapter, but from the area chapter. Another example where you can see that slanting things does not change the area in this case. Same thing for volumes. Slanting shapes does not change volume. Okay. All right. Okay, so there's the volume concept for cylindrical shapes. If they're upright, if they're slanted, if they got a square on the bottom, they could have whatever on the bottom. In every one of these cases, the volume turns out to be the area on the bottom times the height, times the upright height. Okay, that's the definition of volumes for cylindrical shapes. Now, all that is fine and dandy, and it's easy to plug things in there and actually calculate some of these. And there are many examples like that done on the homework. But I want to turn our attention to something slightly more interesting, and that is, what would happen if the shape is not like that? What would happen if as you go up on these cross sections, they get smaller and smaller and smaller and smaller until they end up at a point? For example, what would happen if you were to start off with I don't know, say a triangle on the bottom. So you've got a triangle on the bottom. There it is. And suppose that you've got something that ends up. Whoa. Something that ends up on a single point. So these cross sections on the bottom, you start off with some area A, and the shapes as you go up, they're still the same, but they have smaller and smaller area, although proportional, until they end up in one single point at the top. Then what's the volume? That's the interesting question. And again, the slantiness doesn't matter, but I find it very, very interesting to note that such a volume is 1/3 times the area in the bottom times the height h, where h, of course, is this upright height from here all the way to top. Okay, that's very interesting. Well, the part that's interesting is, where does this come from? 1/3. What the hell? You know. For example, what this is saying is that if you have, for example, let's take a regular, standard, run-of-the-mill cylinder. They go more or less like this. Okay, and we've established that here the volume is equal to the area on the bottom times the height, where of course the height is, again, this height right here. Okay. Now, if we compare that with what I'm saying right now, with the this, by the way, these are called cones. Suppose you start off with the same area as there, but this time you end up with not exactly the same type of cross sections as you move up, but they get smaller and smaller and smaller to end up in exactly one point. And the question that we're contemplating now is, how many of these, suppose you have the same height, by the way, everything else the same. So this is also h. The question that we're contemplating is how many of these pieces, the volume pieces, fit into the cylindrical shape. That's the question, and the amazing result, amazing to me is, or the intriguing is, it's exactly 1/3 times the area times the height, times the area on the bottom times the height. In other words, let's assume the heights are the same and the area on the bottom is the same. Exactly 3 of these fit in that shape. That's what this is stating. And the most intriguing question is why? Where did that come from? How can you figure that out? 1/3. Where did it come from? And so for that, my friends, so this problem may be difficult to attack right off the bat, right off the gate. It may be easier to focus on perhaps a simpler problem. And so ultimately what we want to do is establish this formula right here. Why is this 1/3 business here? And ultimately it might be easier to start off with a different problem. So consider the following problem. What if you had not a circle on the bottom but a triangle? If we could prove it for a triangle, we may have hopes of proving it for other things. So we start off with the assumption here. Suppose you've got a triangle, and we want to establish the following. We want to show that if you got area bottom, A in the bottom. First of all, the slanting doesn't work, so that shouldn't concern you. The slanting principle works the same as before, so we can even assume that these are right angles if you wanted to, or not. That part doesn't matter. This part does matter though. The upright, we will take the upright height to be equal to h. Okay? And so what we want to do is establish why, exactly why, when the bottom is a triangle, why is it that the volume is equal to area in the bottom times the height, not times 1/3. Where is that 1/3 coming from? So that, my friends, amazing where you find solutions in life nowadays. You can learn that from a turnip. So suppose I take this shape, the shape of a turnip, and if you look at it this way, it is, well, if you look at the bottom, it's a triangle, and then it's an upright triangle, so the shape of it is cylindrical. It's very much like these ones that we studied, except, yeah, it's exactly like this one, but maybe more drawn to scale. It looks like this one. See? So the area on the bottom times the height, the entire volume would be area on the bottom times the height. You agree? Where this is the area on the bottom, and this is the height. Alright, that being said, now I sliced it up in a very, very clever way. First I sliced it this way, and then I sliced it this way, and now we have a mess. Well, not really, let me think. These two pieces right here, if I look at them this way, okay? Which one is taller? I'll take a peek. Which one is taller? Nope, not that one. Nope, not that one. Whoa, they're the same height. So you both have the same height. Which one has more area on the bottom? So because the volume... So these two pieces, they have the same area in the cross sections. The only difference is that they're slanted differently. This one is upright here. This is a 90-degree angle, while this one is slanted that way. But if you subscribe to the idea that slanting things does not change the volume, then these two have identical cross sections. If I was to slice them at any single point, they would look like, the slices would look like that. The areas would be the same. The only thing that's different is that they're slanted differently. This one is slanted to the right more, and this one is upright. So that should be persuasive enough to show for most of us that these have the same volume. Okay, so then the other one. Let me see this other piece. How does this piece feel? So I'm gonna leave this one alone and take the middle one. Okay. Now I compare it with this one. I think, whoa, what happened here? But then I turn the shape this way. So if I look at this way and I look at the bottom, which area is more, this one or that one? Well, they're the same area. If I was to take cross sections this way, they would have the same cross sections. And if I measure the height, this would be the height. The height would be the same as on one as on the other. And so again, the only difference between these two, the cross sections are the same. The only difference is that they are slanted differently. So then when you put that all together, these two have the same volume, but those two have the same volume. That would mean that all three of them have to have the same volume. Again, these two have the same volume, these two have the same volume, so all three have to have the same volume. And all three of them make up the entire cylindrical shape. So this guy right here is equal to 3 of these ones. 3 of the shapes that have the triangle on the bottom, and they have a 3 of those. And so this shape right here, that explains it. 3 of these pieces, 3 of these make up an entire shape as such. Okay? Well, you know, they're not exactly 3 of them that are exactly the same shape. Some of them are slanted differently. You take one and you slant it in a different way. You take another copy of it and you slant it in a different way. And you take another copy, slant it yet a different way. And you get these 3. All of them slanted in a different way, but all equal in volume. And all 3 of them together make up the entire piece. And that's why the volume of this is 1/3 times the area on the bottom times the height. That's 1/3 of the cylindrical shape. Okay? That's the first breakthrough. Knowing how to find the volume of a cone that has a triangle on the bottom. And of course that leads to other questions such as, well, what if you didn't have a triangle on the bottom? What if you had a square on the bottom? How would you do that? And that seems interesting for a little bit, but then you realize it's nothing like the other one. This one's gonna be done in a much easier way. So what if you had a square on the bottom, or some sort of quadrilateral? The key to doing that one is breaking it up. You could break it up here, and then find suppose that the entire area on the bottom is, say, A. You break it in half, okay, by using 2 equal triangles here. You break it in half, and now you call each one, I'll call this one A, and I'll call this one B. Then you find the volume of each of those shapes. Now you've made 2 shapes, that each of which is in fact a triangle. And so this would be equal to the volume of this shape, where it has A on the bottom, plus the other shape that has B. Right? And then this one is 1/3 times the area on the bottom times the height, and this is 1/3 times the area on the bottom times the height. I'm calling the area on the bottom here A, and I'm calling the area on the bottom here B. So that gives you 1/3 times the height times A plus B, the area here and the area there. But wait a minute, what is the area A plus the area B? Well, that was 1/3 times the capital A area, the entire area of the square on the bottom. And so lo and behold, it works for squares too, thanks to the proof for the triangle bottom ones. So let me rephrase that. For cones that have a triangle bottom, we've already established that the volume is 1/3 times the area of the bottom times the height. For cones that have a square cross sections, it works exactly the same way, because you could look at it not so much as a square cross section cone, but 2 triangular cross-section cones. So you get that it doesn't have to be a square, it could be a rectangle where A and B could be different. You add up the sum of the areas on the bottom, and you get the entire area on the bottom, and the volume is 1/3 times the height times the area on the bottom. Amazing. But wait, there's more. You could say, well, okay, that's easy for shapes like that. For a triangle, it works no problem. For a rectangle, it works no problem because you break it up into 2 triangles. But what if it was something else? What if it was for example, some crazy hexagon or something like that? What would you do then? Well, the truth is that these are, again, much easier once we've done the one for the triangle. for exactly the same reason that we could handle the one for a square. Because look, you could ultimately break this up into a triangle bottom, another triangle, another triangle, another triangle, another triangle, and you break it up into little areas. You call this one A, B, C, D, E, F, and eventually the total volume could be thought of as the sum of the little pieces. So it's 1/3 times the height times A plus 1/3 times the height times B, all the way to whatever. I don't want to bore you. And then you take out the 1/3 times the H, and that leaves A plus B plus C plus D plus E plus F. And what is it that you get when you add up all these areas on the bottom, A plus B plus C? You get the area of the entire bottom, if you were to call that A. And so the point is that not only does this principle work for, once that we've proved it for triangles, we really have proven it for any type of cone where the bottom can be broken up into triangles, such as a pentagon or a square. But it gets even more interesting, even if you had something that you say you can't really break up into triangles. For example, what if you had a bottom that was a circle? We'll take that. How would you break that up into triangles? Well, one way to do it, there's probably many ways to do it. Here, I'll just pick one thing that comes to mind. One way to break it up into triangles would be to break them up into triangles that look like that. And I know the end over there is not exactly a triangle, but if this is thin enough, it will be. So every one of these lines you could think about as a triangle. Of course, they're thicker at the end, but my pen doesn't. I don't know if I can do that. There. So you could break it up into a million of these triangles, and you say, well, you'll get some error because, for example, here there's a little error. So, well, you should cut it up into thinner ones so that there is smaller error, and thinner and thinner and thinner, and eventually you could cut them up so thin that you could set up an argument using limits, ideas that are slightly deeper than what's usually covered in this class. And the general gist of it is that you could cut it up into slices that are so thin that you will get if you do that indefinitely, you will approach every single time you do it more and more, you will approach closer and closer to the quantity 1/3 times the area in the bottom times the height. Of course, where this is the height, the upright height, and this is the area in the bottom. Amazing. Even things that are not polygons can be broken up into triangles. You may have to use infinite many of them that are infinitely small, but amazingly enough, it still works. And so this is a nice idea. All thanks to stuff like this. Okay, all right, let me take a little break. Okay, so in the exercises, I proposed a very, very famous question, that is, what has more surface area? So we're changing our theme a little bit here. We're going with surface area instead of volumes. And there's this famous question on the homework that asks, which has more surface area? Okay, the sphere, such as this one with, let's just say, radius, I don't know, you could have any radius you want. Let's say radius R. Or would consider the following. What if you had a cylinder that was shaped as such, where the sphere was completely inscribed in there. Let me see if I can make it just a little bit bigger and maybe move it to fit right in there. It's completely inscribed. I know my drawing is not perfect, but take my word for it, it's inscribed. So the question is, which has more surface area, the sphere or the cylinder? The cylinder can be shown to have Let me see, for example, the cylinder has radius r. So all the way around this is 2 pi r. That's the length of the circumference of the cylinder. And this distance right here is r. And that distance right here, from here to here is r. From here to here is r. Therefore, we're all the way to the bottom. Therefore, the height is 2r. So the surface area for the sphere would be... The surface area for the cylinder would be 2 pi r. That's the circumference around the circle, times the height, which would be 2r, which gives you a total of 4 pi r squared. Now the problem on the homework asks a very innocent but super famous question and deep question: which has more surface area, the cylinder or the sphere? And it turns out that they have exactly the same surface area. And there's a very nice argument laid out in the exercises where we go step by step how to derive and how to prove exactly that they have the same surface area, which leads you to the conclusion that the surface area for the sphere must also have 4 pi r square units. So these two have exactly the same surface area, and that's one famous way that one can derive the formula 4 pi r square, super famous formula for spheres. Now, back to volumes. The question at hand now is, if you have a sphere, then what is the volume? That's the question at hand. The volume. After all, this section was intended to be about volumes. So here's a really nice argument that goes back to this thing right here. This should be called the golden goose. You get so much from it. We could do the volume for the ones that have a square on the bottom, for the ones that have pentagon on the bottom, for really the ones that have any sort of bottom on the bottom, because really anything could be broken up into many little triangles. Just imagine, a big box of tiles where all the tiles are triangles. You could tile any floor that someone throws at you with enough triangles. So anyways, this guy right here is good. It's producing results for us, and it keeps on producing till the very end. Here we are with the question of what is the volume for a sphere. Consider breaking up the volume into many little pieces. Let me see if I can make that more straight. Let me see. I can. So make this into many little tiny pieces, and we could have a triangle here at the top or a square, because we know it works for squares too. So I could see if I can make it a little tiny square here, more or less like that. No, whatever. I'll just use a different color. It looks like this. Yeah. That's better. Okay. So that right there, that's a cone. Canonical shape, but the bottom is a square. The cross sections are squares. And the height of it will be the radius of the sphere r. So for this one right here, the little volume, I'm going to call little volume, is equal to 1/3 times the area on the bottom. I'll call it little a. I'll call it little a1, because there will be many, times the height. The height will be r. We already established this. This is just like the one we proved here. That's the kind of shape that we have. We have a canonical shape where the cross sections are rectangles. So the volume is 1/3 times the area of the 1/3 times the area of the bottom times the height. And that's fine and dandy, but then you've got many more everywhere on the sphere, where maybe you have A2 here, some other little rectangle, and the entire sphere can be tiled with this little tiny, super tiny squares, so that each one becomes a canonical shape going into the center, where that's the height of these cones are. And so the volume here. Let me see if I can pull this off. The entire volume would be equal to the sum of all the little volumes. Okay? I'll call them little volume I, because I goes from 1 to, say, infinite many of these. And that would be equal to the sum, as I goes from 1 to infinite many of these. Each little volume is 1/3 times AI times R. The R is the same for all of them. So really, you could, in theory, pull out the R and pull out the 1/3, because you could pull out constants on some of these sums, assuming it's nicely behaved and whatnot. So this could be R over 3 times the sum of all the AIs. And then you say, well, wait a minute, as I goes from 1 to infinity. What is the sum of all the little areas? A1, A2, A3, A4, A5. You got infinite many of these. That would cover the entire sphere. Right? Stop me if I'm lying. Stop me if I'm lying. Right? That would cover the entire sphere. So this guy right here is actually the surface area for the entire sphere, which we just got done explaining. What was the surface area for the entire sphere? 4 pi r squared. That would make this guy right here. Oh man, that would suck if I went through all this and I forgot to hit the record button. But no, I didn't. Alright, where was I? I was about to make magic here. R over 3 times the entire area of the sphere, 4 pi r squared. Whoa, 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 whoa. What is this equal to? 4 times pi over 3 times r to the third. That gives you the world famous formula. Volume is equal to 4/3 times pi times r to the third. That, my friends, that's why they pay me the big bucks. Oh wait, I gotta do this. Of course. There you go. Delivered. They call me the mailman because I deliver volume of a sphere. I am. Let me see. Should we call it a day?